Looking at this wall of polished copper pots, it is easy to take for granted how solid and stable they are. Every inch of this metal is made of the exact same thing, pure copper atoms, stacked together by the trillions. But looking closer, there is a conflict between how that pot behaves and what its atoms are actually doing. Every copper atom has very few electrons in its outermost layer, its camada de valencia. To reach a stable state, these atoms need to lose those outer electrons. Normally, an atom would hand those electrons over to a non-metal atom that needs them, forming an ionic bond. But here, we only have copper. There is no one around to accept the handoff. They cannot share electrons to form pairs either. Even if two nearby copper atoms pooled their outer electrons together, they would still fall drastically short of the 8 needed to satisfy the regla de octeto, the octet rule. This leaves us with a grid where every atom is trying to discard its electrons, but nobody is willing to catch them. By the usual rules of chemistry, there is no obvious reason for these atoms to stay together, instead of crumbling into a pile of dust. This diagram shows the mechanism that resolves that conflict. Instead of seeking a partner for trading or sharing, every atom in the grid releases its outer electrons at the same time. Those discarded electrons do not fly away. Instead, they wash over the entire grid, forming a continuously flowing fluid that weaves through the empty spaces between the newly positive atomic nuclei. The physical structure holds itself together through pure omnidirectional attraction. Each positive nucleus is anchored in place because it is constantly being pulled by the negative charges swirling around it from every possible angle. Chemists call this highly mobile shared cloud the mar de electrons, the Sea of Electrons. In this state, a specific electron no longer belongs to a specific atom. They belong to the entire piece of metal simultaneously, acting as a flexible glue that locks the whole system into place. Looking at this cross-section of a wire, we can see why metals are such effective electrical conductors. An electric current is just moving electrons. In a metal, the electrons in the sea are already loose and in motion. They just need to be shoved to one side. The exact same logic dictates how metals handle heat. When thermal energy is applied to one end of a pan, these free-roaming electrons pick up the vibration and immediately carry it across the grid, even into the handle. Even their brillo, their metallic luster, is a direct result of this structure. When light strikes a metal surface, it hits this dense fluid wall of free electrons and gets immediately bounced back out. This image of factory workers bending strips of steel highlights how metals handle force. They can endure being hammered, bent, or flattened without snapping. To see why, look at the difference in these two diagrams. On the left, a hammer blow to an ionic crystal, like salt, forces matching charges together. They repel each other instantly, and the entire structure shatters. But on the right, when the positive metal nuclei take that same blow, the fluid sea of electrons simply morphs to fill the new gaps. It cushions the shift and holds the atomic layers together. That fluidity is what we call malleability. Whether it conducts electricity, reflects light, or survives being hammered flat, none of these are random traits. They are the physical consequence of how the electrons are arranged. Because this sea of electrons is a liquid, adaptable environment, it does not demand that every positive nucleus inside it be the exact same size, or even the exact same element. This gives us the ability to manually upgrade materials by mixing different atoms into the matrix. We call this a liga metallica, or an alloy. Take steel, for instance. By adding a small amount of tiny carbon atoms into a larger grid of iron, the carbon acts like gravel scattered across a smooth floor. It physically blocks the iron layers from sliding easily over each other, making the metal drastically harder. This photo of ironworkers suspended in the sky shows the result of that microscopic change. Because those atomic layers can no longer slide easily, these beams have the strength to support the weight of a modern skyscraper. Human engineering has relied on this concept for millennia. As seen in these ancient artifacts, early metallurgists mixed copper with tin to produce bronze, creating tools and weapons so durable that they named an entire era of human civilization. We use the same strategy in our kitchens today. By mixing chromium into steel, we get azo inoxidable, or stainless steel. The chromium causes the sea of electrons to form a thin, invisible shield on the surface that blocks rust. Whenever you run an electrical wire, heat a pan, or step into a towering building, you are relying on the mar the electrons. The massive structures we build are dictated by the rules of this atomic glue. Next time, we'll look at how to examine any substance and identify which of these three bonds is holding it together.